Okay, so continuing on, we left off at significant figure rules for addition, subtraction, multiplication, and division. We're next going to talk about significant figure rules for multi-step calculations. So, first and foremost, you perform your multiplication, division, addition, and subtraction operations based on order of operations. So some of you may have heard the abbreviation PEMDAS, so parentheses, exponents, multiplication and division, and then addition and subtraction. You follow the significant figure rules for each step individually. Now, it's really key that you do not round off to the nearest significant figure until you're at the end of your calculation. You carry through your digits to minimize rounding errors. So non-significant digits that we are carrying through calculations can be noted with subscript notation or bar notation. So in this case, 457, the 4 and 5 are significant, while the 7 is not. So any number in lowercase, any number written as a subscript is not significant. Another way of indicating significant digits is via bar notation. And the bar indicates, this little bar above my number indicates the last significant digit. Does that make sense to everyone? Now, why is this important? Well, you're going to encounter multi-step calculations where you have to do a series of operations and you'll have to follow the sig fig rules for each step. So let's look at this example, and this will be a nice refresher. So first things first, we have two values in parentheses. So we'll do the addition operations first. So I'm going to take 143 plus 4.04. Now, my top number has 0 decimal places. My bottom number has 2 decimal places. So then, following my rules for addition and subtraction, how many decimal places should my final answer have? How many decimal places should my final answer be rounded to?
0.
0, yep. So we have 147.04, and we're going to note that we have 0 decimal places by putting a bar over the 7. So this 0 and this 4 are not significant in bar notation. Does that make sense? So this number is equivalent to saying 147. Okay, so let's tackle our second addition operation. So we have 3.550, okay, plus 5, one moment. I'm noticing a small amount of lag in OneNote. So give me 1 second just to correct that lag. Okay, there we go. So we have 3.550 plus 5.4090. Since we're dealing with an addition operation, we care about decimal places. Our top number has 3 decimal places. Our bottom number has 4. So then our final answer should have 3 decimal places. So punching this into our calculator, we have 3.550 plus 5.4090. And that in turn gives us 8.9590, which in turn we round to 3 decimal places, which gives us 8.959. We don't have to use bar notation because the 0 does not affect our calculations if it's a trailing 0. Okay, so now that we have both of our numbers, we're then going to multiply them together. So we have 147.04 times 8.959. And my question to you is, how many digits in 147, when we have a bar over our 7, how many significant digits does 147.04 have using bar notation? How many significant digits does this number have?
3.
3, yep. It has 3 significant figures because anything after the bar is not significant. So we don't care about this 0 and 4 because in our previous calculation, we noted that 147, the significant digits are all of the numbers before the decimal point. So even though we write out this 0.04, so we avoid rounding errors in our calculations, this number only has 3 significant figures. These other digits are just being carried through to complete our calculation. The number on the right, we can clearly see has 4 significant figures. So when we multiply our two numbers together, we should report an answer with 3 significant figures. So we have 147.04 times 8.959, and that in turn gives us 1,317. That in turn, we round to 3 sig figs, which gives us 1,320. Now, you may say, well, this carrying through these digits seems like a lot of extra work. Well, this minimizes rounding errors. And for later examples that you will see, rounding errors can dramatically change your final answer. So, following the rules once again, you perform each operation following order of operations. We had parentheses, so we start with the operation in parentheses. We followed the rules for addition, and we care about decimal places. For 147.04, these last 2 digits are not significant, so we note that by putting a bar over the 7. This bar tells us any number before the bar, including the number under the bar, are significant. So this number is functionally treated like 147. We carry through our non-significant digits in our calculations to avoid rounding errors. And as we see, since we're multiplying, we care about sig figs. The number on the left, 3 sig figs. The number on the right, 4 sig figs. As a result, our final answer needs to be rounded to 3 significant figures. Does that make sense to everyone? So we're putting together the 2 pieces that we've learned in earlier parts of this chapter, and we're combining them together to handle more complicated operations. Any questions that I can address? You're more than welcome to unmute and ask your questions verbally or to ask your questions in the chat. If not, yes.
For that 143, and then there is a dot. So why we put that one there? What it means when we see it?
So the dot at the end it's a more explicit way of noting significant digits. And essentially it's saying, so the main place where this comes up is where if you have a 0. So if you place a dot at the end of your number, a 0 that's between a decimal point and a non-zero number is significant. So the dot is essentially indicating that all of the numbers before the decimal point as their non-zero numbers are significant. It's redundant in this case, but it serves as a placeholder to help us note where our decimal point is.
But it doesn't mean that has a decimal point, right? It means no decimal point.
Well, it doesn't have a decimal place, but you can always put a decimal point at the end of the number. So for example, if we're looking at 140, it has 0 decimal places, but all of these numbers before our decimal point are significant.
Okay.
So the decimal point allows you to explicitly note when a zero is significant or insignificant. It's not as useful when you have non-zero numbers, but it comes into play when you have a trailing zero. Does
So
that make
if we had 140.0, if there was a zero after that dot, then we had one decimal place, right?
exactly?
Okay, got it. Thank you.
So it's a way of representing 0 decimal places while respecting the fact that numbers before the decimal place are treated as significant. Does that make sense?
Yes, thank you.
Perfect. So I see some requests for a few more examples. Don't worry, we have a plethora of examples, and I'll actually start us off, and we'll look at example number 1 just to reinforce what we've learned. So we have a multiplication operation and then addition. So using our order of operations, multiplication comes before addition. So first things first, we're going to deal with multiplication. So we have 5.4 times 2. So this top number has 2 sig figs. The bottom number has 1 sig fig. Since we're dealing with addition, since we're dealing with multiplication, we care about sig figs. So we retain the least number of sig figs, which would be 1 sig fig. So 5.4 times 2 gives us 10.8. However, this 10.8, only one of our digits is actually significant. So this 10.8, you can think of it in terms of sig figs as equivalent to just 10, where we only have one significant figure. However, we carry through these trailing digits to avoid rounding errors. So now what we're going to do is we're going to add 10.8 with a bar over the 1 plus 6. Okay? Now, when performing addition and subtraction, we highlight and we indicate the last place with a significant digit. So 10.8, based on bar notation, only has a significant digit in the tens place. This 0 and 0.8 are not significant digits. 6, on the other hand, has a digit in the ones place. So then, when we add our two numbers together, we get 16.8, and we have to round to the tens place. So following our rounding rules, we look one step to the right, and that in turn gives us a final rounded value of 20. Now, let's unpack this example. So after multiplication, we care about sig figs. We retain the least number of sig figs, which is 2. That gives us 10.8. This 10.8 only has 1 sig fig, so we put a bar over the 1. This 10.8 can be functionally treated like 10 in terms of sig fig rules. So when we add 10.8 with a significant digit only in the tens place following bar notation, with 6, which has a digit in the ones place, we round to the least precise place, which would be the tens place. So we round to the nearest tens place value, which in this case would be 20. Does this example make sense to everyone? So you're following the sig fig rules for each step, and you note the last reported significant digit in each of your numbers using bar notation. This ensures that when you perform multi-step calculations, you're able to account for the significant figures and significant figure rules for each step. Are there any questions that I can address on these examples? Don't be shy to ask your questions in the chat or to unmute and ask your questions verbally. If not, what we'll do is I'll do one more example and then I'll do one more representative example for everyone, and then we'll work on 2 examples independently. So I'll look at example number 14. So let's look at this example in detail. So we have 15 divided by 20.00 minus 5.00. So we deal with the operation in parentheses first. So we're subtracting 20.00 minus 5.00. For subtraction, we care about decimal places. So we have 2 decimal places for each of our numbers. That in turn gives us 15.00. We note that the last reported significant digit in 15.00 is the 0. We don't have to use bar notation in this case because all of the numbers in this measurement are significant digits. Then we're going to move on to division. So we have 15 over 15.00. So looking at our sig fig rules, our top number has 2 sig figs, our bottom number has 4 sig figs. So then our final answer should have 2 sig figs, and we'd write our final answer as 1.0. So you follow the sig fig rules for each step individually, following order of operations. Does this make sense? Any questions on this example?
Professor, why this time it doesn't follow that you keep the place in the what, in the first, in the 5 that
Could you repeat your question?
never mind.
Are you sure? So to elaborate a little bit more, since we're dealing with a subtraction operation, we care about decimal places. So both of our numbers have 2 decimal places. So our final answer needs to have 2 decimal places. So we retain all of our digits up to the 2nd decimal place. And then we use this entire number, 15.00, in our division operation. For division, we care about significant figures. The top number has 2 significant figures. The bottom number has 4. So our final answer should have the least number of significant figures from our 2 measurements, which would be 2 significant figures. Does that make sense?
I have a question.
Yes.
Where did you get the 15 in the division part on top?
It's from this operation right here.
Oh, right. Okay.
So I wrote out each step individually, really just to highlight the fact that when you're dealing with multi-step operations, you treat each step as its own problem and you follow the significant figure rules for each step.
Okay, thank you.
Mm-hmm. So let's take a moment now and let's work on the following 2 examples. Problems numbers 2 and 3 on page 48. We'll spend about 4 minutes on these examples, and let's try to get a few responses in the chat with the correct number of significant figures. And we'll discuss this example in about 4 to 5 minutes. And if you have any questions, don't be shy to type it in the chat or to unmute and ask your question verbally.
Professor, for the 500, is
Yeah.
I guess I'm having kind of like a little brain fart. Would it be 1 significant figure because there's no decimal point at the end of the zeros?
Exactly right. Exactly right.
Okay.
Mm-hmm.
Thank you.
Mm-hmm. And if you have any questions on these examples, don't be shy to ask them in the chat or verbally. And for your responses, please indicate which question, whether 2 or 3, you're responding to, so I can provide feedback. If you have any questions on these examples, don't be shy to type your questions in the chat or unmute and ask your questions verbally. And we'll discuss these examples in about 2 minutes. And remember that even though placeholder zeros are not significant, they indicate whether a number is very large or very small. So make sure to include your placeholder zeros to note whether your number is very large or very small. And we'll discuss this example in about another 1.5 to 2 minutes. Okay, so let's discuss these examples. So first and foremost, we deal with multiplication first and then addition. Okay, so we have 500 times 3.0. 500 has a grand total of 1 sig fig, while 3.0 has 2 sig figs. So then our final answer should have 1 significant digit. So we write out our answer as 1,500 and we put a bar over the 1. This 1,500 is functionally identical to 2,000 in terms of significant figures, but we carry through all of our digits before rounding. We only round at the end of our calculation. So with our 1,500 in hand, which has a number in the thousands place, if we're adding 4.5, which has a number, it has its last reported significant digit in the tenths place, we're going to round to the nearest thousand. So when we get 1,504.5, we're going to round this number to the thousands place, which would give us 2,000. Remember, you need the placeholder zeros to signify that 2,000 is a large number. These placeholder zeros are not significant, but they have a significant role in determining whether your number is large or small. So don't forget your placeholder zeros. Does this first example make sense to everyone? Does this first example make sense? No decimal is included. That's exactly right. The bar indicates the last reported significant digit that you're carrying through in your calculations. So this bar tells us, even though we've written out 1500, the bar tells us only the 1 is a significant digit. The 1 is our last reported significant digit. So this number 1500 is treated as if it had 1 significant figure. Did that address your question? Perfect. So looking at this next example, we have a value and an operation in parentheses. So we'll do parentheses first, followed by multiplication. So if we have 1.5 minus 0.6, so looking, our top number has 1 decimal place, our bottom number has 1 decimal place. That in turn gives us 0.9 with 1 decimal place. We then take 0.9 times 2.0. As you see, 0.9 has 1 sig fig, 2.0 has 2 sig figs. So then, for our final answer, when we get 1.8, we need to round 1.8 to 1 sig fig. We look to the right, we round 1.8 to just 2. Not 2.0, just 2, because 2 has 1 significant figure. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions on these examples? 1.8 is computationally fine, but you then need to round your answer to the correct number of significant figures. Decimal places, where for addition and subtraction, you retain the least number of decimal places. For multiplication and division, you care about significant figures. So a significant figure, you determine the number of significant figures using the rules that we discussed earlier in the chapter. The number of decimal places are the number of significant digits after the decimal point. And then in terms of rounding, to answer the question for rounding, you indicate your last reported significant figure. You look 1 space to the right, and then you check to see whether your number is less than 5 or greater than or equal to 5. If the number after your last reported significant digit is greater than or equal to 5, you round up. If it's less than 5, you round down. Did that address your questions? So let's continue on now, and let's talk a little bit about precision and accuracy. So these words have very unique connotations in chemistry, and it's important that you use these words appropriately in your laboratory discussions and when answering questions both in your lab and lecture. So, accuracy is a measure of how close the average experimental value is to the true or literature value. So we assess accuracy using percent error or percent difference, where percent error is the true value minus the average experimental value over the true value times 100%. These vertical bars represent the absolute value, which means no matter if this number is negative or positive, you always write out the positive value. Percent error is always going to be a positive number. Now, In most cases, the true value is not really known. So sometimes what we do is, instead of assessing our data via accuracy, we assess our data via precision, where precision serves as a measure of the variability or deviation in a data set. So measurements with large numbers of significant figures are considered more precise. So for example, if we look at 50.0 and 50, which of these values would be more precise? Which of these measurements is more precise? Which of these measurements has more significant figures? The first one, exactly. So we have a number with 3 significant figures compared to a number with 1 significant figure. Numbers with more significant figures are generally more precise. Likewise, if precision measures the variability in a data set, how close each of your measured values are to the average of each of your measured values, if we compare these two data sets, which data set is more precise? Which data set has measured values that are closer in magnitude to each other? Which data set, the one on the left or the one on the right, has values that are closer to each other, that are
The right one.
to the average? Yep, exactly right. The right data set has values that is overall a more precise data set, because each of our values are very, very close to our average. Further, there is very little variation in each of our measured values. Compared to the data set on the left, there is a wide variation in our measured values. So this data set on the left would not be very precise. The data set on the right would be relatively precise. So there are a few ways that we measure and assess precision. The first of which is deviation, where we take the average minus the measured value. We can calculate the average deviation and the relative average deviation. We'll focus more on these calculations when they come up in your laboratory report. The main thing I want to impress on you is that there are methods to quantify and clearly indicate precision and accuracy for a data set. And we'll focus on these calculations more as they come up in the laboratory. Just to help everyone visualize in a pictorial sense precision and accuracy, in figure 1, if our goal is to hit the center of this target, all of our data points are very close together, so we can say that our measurements are quite precise. They're clustered together. However, we're not very accurate. In figure 2, all of our data points are pretty close to the center. So we're relatively accurate. However, our data points are pretty spread apart, so we are not precise. Now, ideally, your measured value should look more like figure 3, where we are accurate and precise. Our values match the literature value very closely, and our data points are closely clustered together. Finally, in figure 4, you have a pretty bad data set where we're not hitting the center target and our data points are all spread apart. So we are neither accurate nor precise. So this is how you can visualize accuracy and precision. Accuracy is a measure of how close your data points are to the target value, which is the center. So if all of our data points are very close to the center, we're very accurate. If all of our data points are far from the center, then we're not very accurate at all. Accuracy is a measure of how close your measured values are to the true value. Precision has to do with how close your measured values are to the average, how close your measured values are to each other. If your data points are closely clustered, if they have very similar values, your data set is precise. If your data points are rapidly spread apart, if they have varying values, then your data set is not very precise. Any questions on this idea? And we'll go over and we'll discuss each of these accuracy and precision calculations in more detail in the laboratory, where these are used very commonly. So let's talk next about density and volume. So volume is a measure of the space occupied by matter. It's how much space is occupied by matter. We can calculate the volume of a cube, for example, by taking length times width times height. So volume typically has units of centimeter cubed. 1 cc, which is commonly used in the medical fields, is an abbreviation of a cubic centimeter, which is the same thing as a centimeter cubed. And a cubic centimeter, or a centimeter cubed, is equal to 1 milliliter of volume. So, applying what we've learned, we can actually calculate the number of centimeters cubed in a liter. So if we go from 1 liter to centimeter cubed, setting up our solution map, we can go from liter to milliliter, and then from milliliter to centimeter cubed. So then if we have 1 liter, we know in 1 milliliter, we have 10 to the negative third liter, and we have 1 centimeter cubed per milliliter. So that tells us that we have 1,000 centimeter cubed per every 1 liter. So I'd like everyone to take a moment just to make sure they're familiar with these volume conversion factors. And I'd like you to convert 450 cc's, cubic centimeters, into liters, keeping in mind a centimeter cubed is equal to a milliliter, which is equal to a cc. So let's take about 2 minutes and perform the following unit conversion, and then we'll discuss this example momentarily. And let's try to get a few more responses in the chat before we discuss. And we'll discuss in about another minute and a half. And the responses I'm seeing in the chat look great so far. So let's discuss. So we're going to go from cubic centimeter to milliliter to liter. So we know for 450 cubic centimeters, we have a milliliter per cc. We also know that we have 10 to the negative third liter per milliliter, and that in turn gives us 0.45 liters. Perfect, perfect. So let's keep going now, and let's start to tie volume to density. So density is written as the mass of a sample over the volume of your sample. Density is a physical property, and it's also known as an intensive property, where an intensive property is a property that is independent of the size or amount of an object. Intensive properties only depend on the identity of the object. So the classic example I use is a 1 gram cube of copper. A 1 gram cube of copper will have the same density as a 10 gram cube of copper. So copper has a density of around 8.9 gram per milliliter. If we scaled up and increased the size of our copper cube, and we were looking at a 10 gram cube, it would still have the same density of 8.9 gram per mil. That's because the more of an object you have, the greater the mass of that, the greater mass that you will have in total for that object. So this 1 gram cube of copper would have a volume of 0.1 mils, roughly. The 10 gram cube of copper would have a volume of around 1 milliliter. So as we notice, as we increase the volume of our object, the mass increases proportionally. The density of an object of the same chemical identity will not change when you change the mass and volume. If it's a cube of copper, regardless whether it's a small cube or a large cube of copper, we will observe the same density. Now, what's really cool is that we can use density to differentiate substances, since density is unique for different substances. So if we look at the following picture, we see liquids and solids arrange themselves by density when mixed. The most dense liquid or solid is at the bottom, the least dense liquid or solid is at the top. So looking at this example, we have mercury, which is extremely dense, which has a density of 13.6 grams per mil. Copper has a density of around 9 gram per mil. And water is our least dense substance with a density of around 1 gram per mil. So density only depends on the chemical identity of your object. So let's show how we can calculate density. How do we go about calculating density? Well, to do that, we'd need the mass of an object and the volume of an object. So the mass we can just measure with a balance. That's easy. The volume of an object, however, there are a few methods. The first of which is using volumetric glassware. So for example, suppose you take 10 milliliters of liquid and you find the total mass was 17.50 grams. Well, we can calculate the density by taking the mass over the volume. Note, this is a division operation, so we follow the significant figure rules for division. So we have 17.50 over 10.00. Both of our numbers have 4 sig figs. So as a result, our final answer needs to have 4 sig figs. That gives us 1.750 grams per milliliter for our density. Does this example make sense to everyone? So, mass can also be measured by difference. In this case, you dispense a known volume of liquid to an empty pre-weighed container. So the mass of the sample is found by taking the mass of the liquid in the container minus the mass of the empty container. So step 1, you have your empty container. You record the mass of your container. Step 2, you take your container and you add a known volume of liquid. So you know the volume of your liquid, and in turn, you weigh your container and you get the mass of the container plus the liquid. By difference, we know that the mass of the liquid is equal to the mass of the container plus liquid minus the mass of the empty container. This is known as weighing by difference. So let's look at an example of weighing by difference. So a student found the mass of a 50 milliliter beaker to be 22.500 grams. The student adds 25 milliliters of liquid to the beaker, and they found the combined mass was 47.500 grams. So let's calculate the density of our sample. So density is equal to mass over volume. So the mass of our liquid in this case is going to be the mass of our liquid plus our container minus the mass of the empty container. And as we notice, this is a subtraction operation. So we look and we count the total number of decimal places. In both of these numbers, we have 3 decimal places. Ergo, our final answer would have 3 decimal places. So we get 25.000. Now, if we know the mass and we know the volume of our liquid was 25.00 milliliters, we can calculate the density by taking the mass over the volume. That gives us 25.000 grams over 25.00 milliliters, which gives us 1.000 grams per milliliter. Notice for division, we follow sig fig rules. Our bottom number has 4 sig figs. Our top number has 5 sig figs. So our final answer should have 4 significant figures. Does this make sense to everyone? Any questions on this example? If not, let's continue on. And I'd like you now to work on the following example over the next 4 to 5 minutes. So a student found the mass of an empty beaker to have the following mass. They add 10 milliliters of liquid to the beaker, and they have the mass of the combined liquid and beaker. And I'd like you from this information to calculate the density of the sample. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to submit your proposed questions and responses for this example in the chat, or to unmute and ask your question or share your responses verbally. And let's try to get a few more responses in the chat before we discuss in about another 3 to 4 minutes. And the responses in the chat look great so far. We'll discuss in another 2 minutes. And if there are any questions, I'd be happy to answer them. And don't be shy to submit your responses in the chat. It provides me insight into how the class is doing and allows me to structure my feedback. If not, we'll discuss this example in about 1 minute. So let's discuss this example. So we write out our density equation. So density is equal to mass over volume. Okay, so to calculate the mass of our sample, we take the mass of our beaker plus our liquid minus the mass of our empty beaker. So we follow our subtraction rules. So we care about decimal places. Each of these numbers have 3 decimal places. So our final answer should also have 3 decimal places. Now that we have our mass and our volume, if density is written as mass over volume, we take 20.000 grams and we divide by 10.00 milliliters. The top number has 5 sig figs. The bottom number has 4 sig figs. Ergo, we write our answer as 2.000 gram per mil, so that our final answer has 4 significant figures.
Professor, I'm sorry, I can't see anything. I don't know if it's just me. Whatever you're writing, I couldn't see.
Are other students experiencing a similar issue?
No, I can see.
Okay, you may want to try reloading the Zoom call.
All right.
Yes, I apologize. And just as a note, all of these lectures are recorded, and I also post the recordings and captures of this annotated note set on Canvas once we complete this chapter.
Okay, it's showing up right now. Okay, thank you.
Okay, perfect.
Thank you.
So, Professor, no matter what, because there's 4 significant figures in the answer, there should be, well, in this case, the same amount of significant figures. I mean, the lowest amount of significant figures. So if it's just like 2, then we still have to put the 000.
Yes, just to note that this number has 4 significant figures.
Got it.
Perfect, perfect.
Thank you.
Any other questions I can address? If not, let's keep going now. And let's talk about the alternative method to calculate volume. And this is known as the water displacement method. So we've actually seen examples of this intuitively. If, for example, you've ever been to a pool, you notice that as people jump into the pool, the water level rises slightly. So in the water displacement method, it's based on this idea that objects will displace water based on their volume. So, for example, if we have a beaker containing water or another liquid, what we can do is we can record our initial volume. This is the initial volume of water. Now, if we take an object that has a volume that we'll call V object, and we drop it in to our graduated cylinder or beaker or other piece of volumetric glassware, the water level will rise accordingly. So now that we have our object immersed in the water level will increase, and it will increase based on the volume of our object. So this difference is equal to the volume of our object. So in order to calculate the volume of our object, we take our final volume minus our initial volume. So V final minus V initial is equal to the volume of our object. And that's because our final volume is equal to the volume of water plus the volume of our object. So this allows us to calculate the volume of any object that can be placed in water via water displacement. Does that make sense to everyone? Does this picture make sense? So the change in volume of water is equal to the volume of the object displacing that liquid. So we can rewrite our equation to density is equal to mass divided by V final minus V initial. You need to be careful with your significant figure rules for density, and you need to make sure you follow the rules for significant figures. Does this make sense to everyone so far? So let's look at an example. So a student measured the mass of a metal block, and they also measured the volume via water displacement. So we are looking at the graduated cylinder containing water before and after addition of our solid. I'm just going to draw the solid in. So the first order of business is to record our initial volume. So would someone like to provide me an initial volume reading following sig fig rules? What would our initial volume look like? So looking at our tick marks, we have each of our tick marks. So let's do our classic analysis. So to go from 9 to 10, which is 1 milliliter, takes us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ticks. So then 1 tick is equal to 0.1 milliliters, and a tenth of a tick is equal to 0.01 milliliters. So our initial volume is about at 8.8. So we'd write our initial volume as 8.79, for example, where our first 2 digits are certain and we estimate 1 additional digit. After the addition of our solid, would someone like to volunteer and provide a measurement for the final volume of water in our graduated cylinder after addition of our solid? So looking, we're past the 1, 2, 3, 4, 5. We're past the 6th tick mark. So we'll write our certain digits as 10.6. And then from the bottom of our meniscus, we'll estimate 1 more digit, which would be 7. So we have 10.67 milliliters. So we have our initial and final volume. So now what we can do, now that we have our initial and final volume written to the correct number of sig figs, we can calculate the volume of our solid object by taking our final volume minus our initial volume. As we notice, both of these numbers have 2 decimal places. So our final answer should also have 2 decimal places. So we have 10.67 minus 8.79. That gives us 1.88 milliliters. Following sig fig rules. Now that we have the volume of our object, if we're given the mass of our object, we can calculate the density. So as density is written as mass over volume, we're going to take the mass of 16.91 grams over the volume of 1.88 milliliters. Keeping in mind, based on sig fig rules, our top number has 4 sig figs, our bottom number has 3 sig figs, so our density should be written as our final answer with 3 sig figs. So we get 9.0319 gram per mil. We round this number to 3 sig figs. So looking at 3, 1 space to the right, 1 is less than 5, so we round down, and that gives us 9.03 grams per mil. Does this example of measuring the volume of an object and the density of an object using the water displacement method make sense to everyone? Does this make sense to everyone so far? Any questions on this example? Any questions on this example?
Professor, is that 16.91?
Yes.
Okay. Divided by 1.88?
Yes, exactly.
How did you get 9.03?
So punching in 16.91.
1.88. I'm getting 8.99.
Ah, you're correct. I think I forgot to include one of the digits in the bottom number. So that gives us 8.9946. We look 1 space to the right and we round down, and that gives us 8.99 gram per milliliter.
Okay, I'm like, I'm missing a rounding or something. Thank you.
Any other questions on this example? If not, let's work on and let's attempt a cumulative example for this section on density. So I'd like you to determine the density of this group of marbles if their mass is 97.394 grams. I'd also like you to tell me what is the density of one marble. So your first order of business is to figure out your initial and final volume. And keep in mind, for these pictures, you always need to check and figure out what each of these graduated marks is representing. So let's spend 5 to 6 minutes on this cumulative example, and then we'll discuss this example together. If you have any questions at all on this example, don't be shy to ask them in the chat or to unmute and to ask your questions verbally. And really pay attention to getting a accurate volume reading. Always make sure and go through and figure out what is the value of each of these little tick marks. That's my major hint to you. And let's try to get a few more responses in the chat, and we'll discuss in about another 5 minutes. And if there are any questions, don't be shy to ask them in the chat. Let's try to get a few more responses for the density value, and then we'll discuss this example momentarily. Make sure you're paying attention to significant figure rules for measurements from graduated devices and in your subtraction and multiplication operation. Let's try to get a few more responses in the chat, and we'll discuss in about another 3 to 4 minutes. And the responses I'm seeing in the chat look reasonable so far. Just make sure you're following the significant figure rules and paying attention to the significant figure rules for subtraction and division. And we'll discuss this example in about another 2 minutes. And if you have any questions at all, don't be shy to ask them in the chat or unmute and ask the question verbally. We'll discuss in about another 1 minute. Okay, so let's discuss this example. So first we need to figure out the value of a tick. So to go from 70 to 90 takes us, so 20 mils takes us 10 ticks. Ergo, 1 tick is equal to 20 over 10, which is 2 milliliters. A tenth of a tick then is equal to 2 over 10, or 0.2 milliliters. Okay, perfect. So now that we know what a tenth of a tick is, from the bottom of our meniscus, we are 1, 2, 3, 4, 5. We're about 5 ticks up, which corresponds to 60. We can estimate an additional digit, so I'm going to say 60 point. I'd say about 60.8. Since it's not quite at it's not quite at the tick for 62. So that's my first initial volume reading. So for V final, past 90, we are 1, 2, 3, 4 ticks up. So I'd say it's about 98.8 milliliters, since we're not quite at the 5th tick yet. So to calculate the volume of our marbles, we have 98.8 milliliters minus 60.8 milliliters, and that in turn gives us 38.0 milliliters, respecting the fact that each of these numbers, 60.2 would also be okay, yes. So respecting the fact that each of these numbers have 1 decimal point, our final answer has 1 decimal place. Now that we know the volume, if we know the mass, we can calculate the density. So the mass is 97.394 grams. So then the density is equal to the mass over the volume. So 97.394 grams over 38.0 milliliters. That in turn, so the number on the bottom has 3 sig figs. The number on the top has a massive 5 sig figs. Our final answer should have 3 sig figs. That gives us 2.563 gram per milliliter, which we then round to 3 sig figs. 3 is less than 5, so because of this, we round this number to 2.56 grams per mil. So make sure you follow the significant figure rules when calculating density via water displacement. Are there any questions that I can address on this example? Now, as our final sort of important question, we measured the density of 3 marbles. The density was about 2.56 gram per mil. What would the density of 1 marble be? What would the density of 1 marble be? And think it would be the same, exactly right. The density doesn't depend on the amount of an object. It only depends on its identity. So the 3 marbles has the exact same density as 1 marble. That's a really important point for density. Now, one thing I do want to show you is a way to check your work. How do we check our work? So one way that you can check your work is you can calculate the mass from the density and the volume. So mass is equal to density times volume. So we can take the density that we've calculated, multiply it by our volume, and this allows us to check that we've done everything correctly. Because as we see, we get out about the same mass. So we haven't made a major calculation error. There will be a few differences due to rounding, but you just want to make sure that from your calculated density, you can recalculate your mass. Likewise, you can also check your work by recalculating the volume. And to calculate the volume, you just take the mass over the density. So you take 97.394 grams over 2.56 gram per mil. And that in turn gives us a volume of 38.0 milliliters. So for when you're taking an exam, you might as well check your calculations by recalculating your mass and volume. That way, you're always 100%, you're always more confident in your results because you've verified that your density can be used to recalculate the mass and volume that you measured in the problem. Does this idea of checking your work make sense to everyone? It's a nice trick, and it's a nice way to have more confidence in your submitted results. If you start getting wildly different answers when you recalculate your mass and volume, then I would go back and check your work once again. So, are there any other questions on these examples? Any other questions on these concepts in Unit 1? So, this is the end of Unit 1. So what we're going to do now is I'd like everyone to please get out your Unit 2 notes. And for the student, so just as a side note, I'll be sending out further ad codes today as there are a few additional spots. And I'll be sending these Unit 2 note link for the waitlisted students later today. Just as a side note, once again, the Unit 2 notes are found in Canvas under the Week 2 module. So if you don't have them, make sure to pull them up at this time. I'll give everyone about another 2 to 3 minutes to pull up the note set, as this next chapter really is sort of the backbone of chemistry, and concepts that we see here in chapter 2 will be applied again when we get to our chapters later in this course on organic chemistry. Can I get some confirmation in the chat that everyone is able to find these notes in Canvas and that everyone is able to access these notes in Canvas if you're enrolled in the course?
Yes.
Perfect, perfect. Okay, perfect. I always want to make sure we have our reference note sets in front of us when we go through these lectures. So let's start, and what I'm going to do is I'm going to create a separate recording for this.